Right now, as you are watching this, a machine built before the internet existed is sitting in the space between the stars, and it is listening to something that nobody on Earth has been able to explain. It has been listening since 2017. A faint, narrow, steady tone in the plasma outside our solar system. Not a burst, not a glitch in an old instrument. A hum that has now been recorded continuously across more than 10 times the distance between the Earth and the Sun. The scientists who published it in the journal Nature Astronomy were careful with their language, and there is a reason for that care. There are two possible physical explanations for what that signal is. One of them fits comfortably inside the physics we already have. The other would mean our picture of the space between stars is wrong in a way that would take years to rebuild. And here is what turns this from a strange footnote into something with a clock attached. The only instrument in existence that could settle the question is dying. It loses about 4 watts of power every year. Its instruments are being switched off one at a time permanently by engineers who know they cannot turn them back on. Today we are going to walk through exactly what Voyager 1 found out there, why those two explanations lead to completely different versions of our galaxy, and what happens to that unanswered question when the last instrument finally goes dark. Before we begin, have you ever stood outside at night and tried to picture something we built still moving out there? Comment what you saw and where you were watching from. Subscribe for future alerts and help us reach 15,000 likes so this information reaches someone who needs to hear it. When the next discovery breaks, you will not have time to search for answers. That is why I created this 3-book cosmic survival series covering asteroid threats, solar storms, and what to do when the sky stops behaving the way it should, how to prepare, how to survive, and how to rebuild. Scan the code or check the description. It might be the most important purchase you make this year, but this is not an advertising show, so let us begin. Start with where the thing actually is, because the numbers do most of the work here, and they are worth sitting with for a moment. Voyager 1 is currently a little over 15 billion miles from Earth. That number is almost useless as a mental image, so try it a different way. A radio signal traveling at the speed of light, which is the absolute ceiling on how fast anything in this universe can move, takes roughly 22 to 23 hours to reach it. Send a command on Monday morning and the spacecraft does not hear you until Tuesday morning. Its reply does not land on Earth until Wednesday. 2 days for one exchange. That is the fastest possible conversation you can have with it, and no engineering improvement anywhere in the world can shorten it, because the limit is not our technology. The limit is physics. It runs on about 4 watts of usable power for its science instruments. 4 watts. The bulb in your refrigerator draws more than that. The whole spacecraft, every heater, every transmitter, every surviving instrument is now working with a total supply of roughly 250 watts. Down from about 470 watts when it launched. And it launched on the 5th of September 1977. Think about what that date means in engineering terms. There were no personal computers in ordinary homes. The memory on board is measured in kilobytes. The design brief was to fly past Jupiter, fly past Saturn, take photographs, take measurements, and then go quiet. NASA expected the mission to be finished somewhere around 1981, 4 years. Maybe 5 if they were lucky. It passed Jupiter in March of 1979 and sent back the first close images of that planet anyone had ever seen. It passed Saturn in November of 1980 and used the gravity of each planet to fling itself faster and further outward, and then it did not stop. It kept transmitting through the 80s, through the 90s, through the 2000s, past every deadline anyone had written down for it, until it reached the one boundary that made the whole story change shape. On the 25th of August, 2012, Voyager 1 crossed the heliopause. If that word is new to you, it is the most important edge in our entire cosmic neighborhood. So let me explain exactly what it is, because everything that follows depends on you having this picture clearly in your head. The sun does not only give off heat and light, it constantly blows a stream of charged particles outward in every direction, and that stream is called the solar wind. It leaves the sun and it keeps going, pushing outward, past Mercury, past Earth, past Jupiter, past Pluto, inflating a vast bubble around the whole solar system. That bubble is called the heliosphere. Everything you have ever heard of lives inside it. Every planet, every moon, every asteroid, every comet, every spacecraft we have ever launched, and every living thing that has ever existed anywhere. But the solar wind does not blow forever. Eventually, it runs out of pressure, and pushing back against it from the other side is the interstellar medium, the thin gas and dust and plasma that fills the space between stars, which has its own pressure and its own magnetic field. There is a place where those two pressures balance out and the solar wind finally stops. That surface is the heliopause. It is the physical outer wall of our solar system. Everything inside it belongs to the sun. Everything outside it belongs to the galaxy. And in August of 2012, one machine crossed that wall and came out the other side, and then it kept transmitting. That is the thing to hold on to. We do not just have a spacecraft that once left the solar system. We have a live scientific instrument sitting inside interstellar space right now, sending back measurements of an environment that no telescope on Earth can measure directly, because a telescope on Earth is looking at the interstellar medium from the inside of a bubble that distorts everything about it. So what did it find? Start with the magnetic field, because this is the one that surprised people the most, and it is the one that gets talked about the least. For decades, one of the strongest predictions in this whole field was about what would happen to the magnetic field at the moment of crossing. Inside the bubble, you are inside the sun's magnetic field, and the sun's field has a particular direction and a particular structure that is well understood. Outside the bubble, you are inside the galaxy's magnetic field, which is a completely separate thing produced by completely different processes on a completely different scale. Two different fields, two different sources, two different orientations. The model said the transition should be obvious. As the spacecraft crossed, the direction of the magnetic field should swing round sharply and unmistakably from one orientation to the other. That rotation was going to be the flag on the map. That was how we would know for certain we had crossed. It did not happen. The particle measurements changed exactly as expected. The count of solar particles collapsed, the count of galactic cosmic rays, the high-energy particles that come from outside and that the bubble normally screens out jumped upward. Every plasma reading said the same thing and said it clearly. We were out. But the magnetic field direction barely moved. Take a second with that, because it is genuinely odd. The spacecraft left one magnetic environment and entered a completely different one, and the compass needle, so to speak, stayed pointing in roughly the same place. That is not a small discrepancy at the edge of the data. It is a direct contradiction of a specific, confident, decades-old prediction, and it came from the only instrument that has ever actually been there to check. The leading explanation now is that the two fields are not separate at all in the way we assumed. The sun's field lines, dragged outward by the solar wind and squashed up against the boundary, appear to be linking up with the galaxy's field lines through a process called magnetic reconnection. Reconnection is what happens when magnetic field lines from different sources meet, break, and reattach to each other in a new arrangement, releasing energy as they do it. It is the same basic process that drives solar flares, just happening at the outer wall of the solar system instead of on the surface of a star. If that is right, then the boundary of our solar system is not a wall at all. It is a seam, a place where the magnetic field of our star and the magnetic field of the galaxy are stitched into each other and exchanging energy across the join. And that matters for a reason that reaches all the way back here. The heliosphere is not just a scientific curiosity, it is a shield. Galactic cosmic rays, the high-energy particles produced by exploded stars scattered across the galaxy, are genuinely dangerous to biology. They break molecules, they damage genetic material. The heliosphere deflects a substantial fraction of them before they ever reach the inner solar system, and the Earth's own magnetic field and atmosphere handle much of the rest. If the outer boundary of that shield is more connected to the galaxy than we thought, more permeable, more variable over long stretches of time, then the amount of radiation reaching this planet over geological timescales may have moved around more than our models allow for. Nobody is saying that shield is failing. It is not. But the question of how stable it has been across millions of years is now a live one, and it became live because of one machine that was supposed to stop working in 1981. Now let us go to the second finding. And this one has a dramatic nickname attached to it that I want to handle honestly, because the honest version is more interesting than the exaggerated one. At the boundary region, the temperatures Voyager 1 measured were somewhere in the range of 30,000 to 50,000 degrees Celsius. The surface of the Sun is around 5,500 degrees Celsius, so the outer edge of our solar system, the empty dark nothing at the far end of everything, measured several times hotter than the surface of the star at the center of it. Some coverage has called this region a wall of fire, and you will see that phrase used a lot. Here's the part that phrase leaves out, and it is the part that actually teaches you something about physics. Temperature is not the same thing as heat. Temperature measures how fast individual particles are moving. Heat measures how much total energy would actually transfer into something you put there. Out at the heliopause, the particles are moving extraordinarily fast, so the temperature reading is enormous, but there are almost none of them. The density is so low that Voyager 1 sitting directly inside this so-called wall of fire did not get hot. Its instruments recorded the temperature of the particles around it, while the spacecraft itself stayed cold, because in any reasonable stretch of time, only a handful of those particles ever actually hit it. If you could stand out there, you would not burn. You would freeze. The region is technically at 30,000 degrees, and it would still kill you by taking your heat away, because there is nothing there to give any back. I want to be clear about why I'm spending time on this. It would be easy to just say wall of fire and move on, and it would get a bigger reaction. But the real result is better. Voyager 1 found a region where the particles are moving at speeds we did not predict, carrying energies we did not predict, in a boundary zone whose structure we did not predict, and it found this by being the only object that has ever physically been inside it. That is the discovery. It does not need to be dressed up. Which brings us to the thing this whole video is really about. In 2017, 5 years after the crossing, the plasma wave subsystem on board Voyager 1 started picking up something nobody had planned for. The plasma wave subsystem is an instrument designed to detect oscillations in the surrounding plasma. Plasma is gas that has been stripped of its electrons, so it is made of charged particles, and charged particles do something that neutral gas does not do. They push and pull on each other electrically. Disturb a plasma and it rings, the way a struck bell rings, and the pitch of that ringing depends directly on how densely the particles are packed. Denser plasma rings at a higher frequency. Thinner plasma rings lower. That relationship is the whole reason this instrument exists. If you can measure the frequency, you can calculate the density. And the density of the interstellar medium is one of the most basic numbers in all of astrophysics, because almost everything about how gas moves through a galaxy, how stars form, how supernova shock waves travel, depends on knowing it. Before 2017, we had a handful of these measurements, and they came in bursts. Every so often, a large eruption on the Sun would send a shock wave all the way out past the heliopause. That shock wave would smack into the interstellar plasma. The plasma would ring, and Voyager 1 would record the note. Then silence, sometimes for a year or more, until the next one arrived. It was like trying to work out the climate of an entire continent by checking one thermometer once a year. What started in 2017 was different. The instrument began recording a tone that did not go away, not a burst, not an echo of a solar event. A weak, narrow band emission that simply stayed there, month after month, year after year, while the spacecraft kept moving further out. Stella Ocker, then a doctoral researcher at Cornell University, identified it in the data, and the analysis was published in Nature Astronomy in 2021. By that point, the emission had been tracked across roughly 10 astronomical units of interstellar space. One astronomical unit is the distance from the Earth to the Sun. So this signal has now been recorded continuously across a stretch of the galaxy, more than 10 times the width of our own orbit around our own star. And what it shows is that the interstellar medium is not smooth. Every model built from Earth described the space between stars as quiet, thin, cold, sparse, mostly featureless, with the interesting activity confined to nebulae and shock fronts and other specific structures. In between all of that, the model said there is essentially nothing happening. The continuous measurement says otherwise. The density is not constant. It varies as the spacecraft moves through it, on scales from very small up to enormous, which means the interstellar medium has structure, it has texture, it has something that behaves like weather, and it has that weather in the regions we assumed were empty. We did not detect this earlier for a straightforward reason. You cannot see it from inside a bubble. Every instrument humanity has ever built, apart from two, has been sitting inside the heliosphere, looking outward through a distorting medium. We were reading the interstellar medium, the way you read the shape of a room through frosted glass, and we had built an entire theoretical picture out of that reading. Now, before we get to the two competing explanations for that hum and why the difference between them matters so much, there is a stretch of this story that nearly ended everything, and it happened much more recently than most people realize. In November of 2023, Voyager 1 stopped making sense. The signal was still arriving, the carrier tone was there on schedule from 15 billion miles away, but the data riding on that signal had turned into a repeating pattern of nonsense. Not a message the team could not decode because it was damaged. A pattern that carried no information at all, endlessly repeating, arriving faithfully every day from a spacecraft that was clearly still alive and clearly no longer able to say anything. For a team that had been running this mission successfully since 1977, this was new. Working out the cause took months, and the answer, when they found it, was almost cruel in its simplicity. A single chip inside the flight data system had failed. One component, storing a portion of the software responsible for packaging up science data for transmission, had degraded after 46 years of continuous bombardment by cosmic radiation. No alarm had gone off. Nothing had warned anyone. The chip had simply stopped holding its contents correctly, and the code stored on it had become garbage, and the spacecraft had gone on faithfully executing garbage. In any normal engineering situation, you replace the part. Here, the part was 15 billion miles away, unreachable by anything that exists or that anyone has proposed building, and the only tool available was a radio signal with a 22-hour delay in each direction. So think about what the working day actually looked like at the Jet Propulsion Laboratory during those months. You study the data, you form a theory, you write a set of commands to test that theory, you transmit them, you wait 22 hours for them to arrive, you wait another 22 hours for the response, you read what came back, and it is slightly different from what you expected. So your theory is partly wrong. You revise it, you write new commands, you transmit, you wait another 2 days. And through every one of those cycles, you are carrying the knowledge that a single badly chosen instruction sent once could end the mission permanently with nothing to be done about it afterward. They did it anyway, and they solved it. The corrupted memory could not be repaired, so they did not try to repair it. They worked out that the affected code could be broken into smaller pieces and stored elsewhere in the spacecraft's remaining memory. Each piece had to be individually adjusted so that it would still run correctly from its new address, because code written for one location does not simply work in another. Then all the pieces had to be linked back together so that the whole thing functioned as one program again. They performed this remotely in stages through a 44-hour round-trip delay on a computer designed in the early 1970s, using documentation written by engineers, who in many cases had long since retired or died. In 2024, Voyager 1 came back, clean data, readable science, and what it immediately started sending again was more of that same persistent hum from the interstellar plasma, more measurements of the structure that the models had never predicted, as if nothing had happened at all. Which brings us back to the question at the center of this, and to why it has not been answered yet. The persistent emission has two candidate explanations, and researchers analyzing the data have been open about the fact that they cannot yet tell which one is correct. The first possibility is that it comes from thermally excited plasma oscillations. In plain terms, the plasma is warm. Warm things jiggle, and charged particles jiggling around are enough on their own to make the plasma ring quietly and continuously at its natural frequency. Under this explanation, the hum is the background sound of interstellar plasma simply existing at its own temperature. This would be a real and valuable discovery, and it would mean the first continuous density measurement in history, but it would sit inside the physics we already have. We would learn a great deal, and we would not have to tear anything down. The second possibility is something called quasi-thermal noise. This is a different mechanism in which electrons moving past the spacecraft's own antenna produce a signal whose shape encodes both the density and the temperature of the surrounding plasma. The important part is that the two mechanisms do not produce identical signals. They imply different relationships between what the instrument records and what is actually out there. If the emission is quasi-thermal noise, then the numbers we would extract from it are different numbers, and the existing description of the interstellar medium would need substantial revision. So the question is not whether the hum is real. It is real. It has been recorded for 9 years across 10 astronomical units. The question is what the hum is telling us, and the two available answers point at two different galaxies. Settling it requires more data. Specifically, it requires measurements across a wider range of frequencies and measurements of the electron temperature taken at the same time as the density, so that the two explanations can be told apart by comparison. And that is where the clock comes in.